Okay. Hello. Hi there. Hello. And welcome to chemistry. Right, look. I'm going to be totally honest here. I am ultimately torn between chemistry at this point, right? I don't know whether to love it or hate it. Now, the exams are okay. AQA this year has been really nice, which is... It's suspicious that they're being this nice. I mean, even EdXL's been pretty bad. I wonder if they're doing this because they're kind of willing to ease everybody back into exams after COVID. So in a way, we've gotten really lucky. I'm pretty sure last year's Year 11s had horrible exams. They hated it. The advanced information was all bullshit, so they ended up getting a bunch of stuff wrong. I felt bad for them, you know. But anyways, look, the truth be told is I have to make a choice between picking history and chemistry for A-level. And I am so torn, it's unreal. I don't know whether to pick history because it's a very interesting subject. A lot of interesting things you cover in sixth form. Or whether to pick chemistry. It would go well with biology, and it's, again, an interesting subject, but it is a lot more difficult, I would argue. I would argue chemistry is a lot more difficult. Paper 2, which is what we're doing, is probably the easier of the two papers. You have two really nice geography topics. You have organic chemistry, which it's okay. It's not the best, not the worst. You have chemical tests, chemical analysis. So in conclusion, I would argue that chemistry paper 2 is nice. Now, I'm just going to go send everyone the link to the stream before we actually get on and start revising. I want to make sure people are here. We'll start off with chemical analysis. And the reason we'll do that is because I am pretty sure that chemical analysis takes up maybe 10% of a paper, possibly more. It is normally, in all the mocks that I have seen, it is normally scattered in amongst the paper. So you might get a question on gases, and chlorine will be there. How to do a chlorine test. You might get a question on flipping, I don't know, the Haber process, and it might ask you how would you test for hydrogen. So chemical tests are kind of a building blocks of this paper. Right, I've sent everyone the link. I'm gonna go into DMs even and send it to Kieran and Ashton. I'll just put, in case any of them want to join. So, let's start with chemical analysis, because like I said, that's the topic where they can put anything in. They could link it to reversible reactions, they could link it to organics, they could link it to anything. I'm going to go through all the ones I know, and then I'll look at some flashcards that I've made to make sure I haven't missed anything. Number 1 is flame tests. Now, we all love flame tests because they're fun. Okay. Let us go. Oh, bro's already doing it. Okay. So, you need to know how to also set it up. So, yeah, Kieran's right. Lithium is crimson, sodium is yellow, potassium is lilac, and copper is green. It is easy, and I know Alex even got this mixed up. It's easy to get copper mixed up with blue, it being blue, but that's for hydroxide testing. So that is hydroxide testing. Iron 3 being green. That's hydroxide testing. That is not flame testing. I'm pretty sure. Because I'll get onto hydroxides in a minute. But for flame tests, how you would set it up is you would use a wire, like kind of a loop, and this needs to be something unreactive. Set it on the front. Oh, it did? Huh. I don't think we did that in class. You might be. I don't have the PowerPoint with me, but I'll take a look in a little. But I'm pretty sure that's hydroxide. So you need a loop, like a little wire. It needs to be unreactive because if it's reactive, you're gonna get a different color flame, aren't you? So this is gonna be nichrome, which is a combination of nickel and chrome, which is unreactive. Thing I didn't even know, you clean it with hydrochloric acid to make sure that you don't have any excess. If you tested copper and then you test it with potassium, you're making sure that the flame is potassium. So you would get your little Bunsen burner. You would put the loop in the hot part of the good formatting. You would put it in, and yeah, it would change color. You would put it in. I'm assuming it's the. I can't remember. Is it the blue part of the flame, or is it the outer part? I always get that one mixed up. I'm pretty sure it's the inner hotter part, but you guys might have to correct me on that. I don't recall. What else do we need to... Well, we need to know the colours. So, I just put red, but I'm pretty sure it's crimson for lithium. Potassium is going to be lilac or purple. That's an easy one to remember. Purple potassium. Sodium is yellow, I'm pretty sure. And copper is green. So those are like the ones you need to know. I'm pretty sure, yeah, Luke said barium is red. I don't know if we need to know that, but, and yeah, there are different types, that's the problem. Different ions. So copper 2 is blue and green. Oh, okay. I see. Ah, okay. Right, I was gonna say, flame tests for iron. Oh, interesting. I didn't know that you did flame tests for iron. Huh. Interesting. I don't think we've done that in class. That must have been something only on the PowerPoint. Because, yeah, I thought you were on about hydroxide testing there, which I think is the next one. So flame tests are for, like, metal ions, but then you would also do hydroxide. I'm pretty sure that's what you call it anyways. Hydroxide tests. And I can't recall what you used to test it, but I'm pretty sure it's sodium hydroxide. Please correct. In fact, I might be able to correct myself here if I. Nope, I have no idea where my flashcards are. Okay, you guys might need to correct me there, but I'm pretty sure we use sodium hydroxide, and that is for one where it forms a precipitate. A precipitate, which I'm pretty sure is an insoluble solid. Precipitate is insoluble solid. So, for hydroxide testing, you're looking at things like aluminium, magnesium, calcium, copper, iron 2, and iron 3. Now, dilute, right. So for these three, aluminium, magnesium, and calcium, if you add your sodium hydroxide, it will go white, it will form a white precipitate, but in order to differentiate between aluminium and the others, if you add excess of aluminium, it will go colourless. I'm pretty sure. Copper is blue. Now, iron. I always get these mixed up. Is iron 2 brown and iron 3 green, or is it the other way around? I can't really recall that, but because I think if I recall, 3 would be thing. But that's I think all you need to know for hydroxides. Copper 2, blue. Iron 2 is green. Okay, yeah. I always kind of remember it as almost like the colours being washed out. Obviously, that's not what happened, but that's how I remember the colours. It goes from like green to kind of a washed out, so a brown. So there you go. So hydroxide tests and flame tests. Probably the two easiest ones to really remember. What else is there? There is halide tests. We can quickly go through them because I think they're also just dead easy. There is quite a few. Well, no, there's only 3. What do you use for halide tests? Oh, I know it, but I don't. I've totally just forgotten. Halide testing. Is it? I need to know now because it's on the corner of my mind here. It's actually annoying. Hang on. Halide testing. Oh, it's silver nitrate. Yes, it's silver nitrate. Oh, bollocks. I knew that one. But see, that could have been 1 or even 2 marks in an exam for if it said, how would you test the presence of bromine? So, I think it's chlorine? Fluorine? No, hang on a minute. I don't recall what fluorine is, but I think it's chlorine, iodine, and bromine. Now, they all form precipitates. Chlorine is a white precipitate. Bromine is a cream. And iodine is a brown or an orange, I'm pretty sure. I do not drink silver nitrate. Does fluorine have one? I think even on the PowerPoint. Yeah, fluorine is no precipitate. Chlorine is white, bromine is cream. Oh, it's yellow. I was right in the middle there. I guess think of, because obviously iodine's orange, just think you're slightly adjusting the hue of it so it becomes yellow. I don't know what colour bromine is, but it's cream. Iodine ions give yellow precipitate. Right. We were close. So that's halide testing. Now, I feel like I'm missing... There is a test for something involving... There is a test for... Oh, Ashton's asking... Can we request certain topics? I'll just put sure. I'm pretty sure there is a test where you use barium chloride, but I don't know what that is. If someone could try figure that out, I'll list for other ones. So there's hydrogen testing. There's the chlorine testing, which I guess is separate from this one. Oxygen test, and there is carbon dioxide. Now, a lot of these are really easy to remember, but it's the technical terminology that people always get wrong. So for carbon dioxide, barium chloride, yes, it's sulfate ions. So barium chloride, you get your hydrochloric acid. Okay, yeah. So it's hydrochloric acid. I'll just put HCl plus barium chloride. And that's for sulfate. Thank you. That I totally forgot that was a thing. I think that was on one of our mocks, and nobody, like, barely anyone got it. But again, like I was saying before, you could literally get up to maybe 10, 15 marks in an exam because of little questions that are just, put through about testing. Like in the Harbour process, you could get a question on how do you test for hydrogen. You could get a question on chlorine. That would be a really nice one. In fact, I'm pretty sure I've seen that question like 5 times in a mock. You could get oxygen, like literally anything. Probably more likely to get these two in the chemistry of the atmosphere, testing oxygen. But anyways, carbon dioxide turns lime water milky. But I don't know whether you would get that. You might get 1 mark if it's a 2-mark question, but I think the technical terminology is when carbon dioxide gas is bubbled through calcium carbonate, a white precipitate is formed. So you just add that tiny bit of detail. Yes, cloudy, that is it as well. So to get all 3 marks, I'd probably say when bubbled through calcium carbonate, a white precipitate is formed, making it go cloudy. To be fair, I just hear milky, like, when talking about it, because I don't know, there's just some funny words in science I always remember, like flipping spongy mesophyll and, cream precipitate, just like the kind of funny words, so that's one I remember. With oxygen, that is the one where it relights a glowing splint. Now, again, I'm not sure whether that's the correct terminology, but in other words, in the presence of oxygen gas, a splint which isn't completely, I guess, burnt out. Oh, phenolphthalein. I never have talked about phenolphthalein in any of the exams. I talked about another one instead. What was it? Methyl orange. I talked about that in the chemistry test, but I didn't know what colour it went before and after, so that was a little awkward. I was smart the examiners, but I didn't know what colour. I think it goes yellow to orange, but I put orange to yellow, so goodbye my grades. But yeah, with oxygen, it relights a glowing splint. But I guess that's kind of how forest fires and stuff happen, in a sense, because, if you have a bunch of trees, the fire, I think we learned this in Year 9 Geography, oxygen is almost the fuel that the fire uses to keep on spreading. The wind and stuff also kind of helps. So that's a decent way of remembering it, I guess. Just think forest fires. Chlorine, that is the one that we did with Miss Ford, who, little side rant here, but oh my god. Miss Ford moment. Like, seriously, I have not known a teacher as sarcastic as her. And not even in a good way, where, like, she makes kind of light-hearted jokes and stuff, makes fun of people, like, literally just, like, taking the piss out of people and getting mad when people aren't, like, grade 9 students. Like, bro, I feel bad for Faith, right? I overheard her once talking, because I sit next to her in physics. Exactly. Faith, she was talking about how, like, because of the stress of exams, she literally some days can't wake up because the night before she can't sleep, so she has to take a bunch of, like, drugs to, like, go to sleep and stuff, which is, like, awful. That's a terrible thing. And Miss Ford literally was like, oh yeah, Faith, just because you can't wake up in the morning and go to school, like, bro, don't say that to somebody, like, bro. Like, that's fucked up. Why would she say that? I'm literally making fun of somebody for, getting flippin' overworked with exams to the point of, like, taking drugs and stuff. Like, bro, you don't say that. But anyways, that was my little side rant. But yeah, Miss Ford, mid-teacher. Not to be offensive or anything, but personal opinion, legally I'm allowed to say that. Okay, legally I'm allowed to say that. I will be just a second. I need to adjust my... Right, I'm back. She said, yeah, so exactly, she seems to make being sarcastic a whole personality. It's not a good trait, really. You know, especially when you're a fucking teacher, and yet you insult half the pupils that you teach. Like, Jesus Christ. The only reason I am close to not picking chemistry is because if I get her, it's over. I'm instantly dumping chemistry. Anyways, you guys know these ones, right? So chlorine, it bleaches the litmus paper. And technically, you would have to say, oh, it goes from blue to white, but nobody really cares. Just say bleaches it. And then, and then hydrogen is the squeaky pop test. And for 3 years straight, I unironically thought it was called the squeak and pop test. Which is a little awkward, but it's squeaky pop. So in the presence of hydrogen gas, a glowing splint will create a squeaky pop noise when in the presence of it. What is Ashton saying? Ashton said, nice, thanks. Alright, nice. So yeah, that is kind of it, guys. So, let's do a quick recap. Sulfate ions, you would test them with barium chloride, with hydrogen and chlorine, hydrochloric acid, squeaky pop for hydrogen, glowing splint for oxygen, litmus paper for chlorine, calcium carbonate, white precipitate for carbon dioxide. Flame tests, use an unreactive wire, dip it in hydrochloric acid to clean it, red for lithium, yellow for sodium, purple for potassium, green for copper. For hydroxide testing, you would use sodium hydroxide, you would do iron 2 green, iron 3 brown, copper blue, aluminium, magnesium, and calcium are white, but in excess, aluminium goes clear. That is it. I'm pretty sure. Is that everything? Oh, halide testing, you got white, cream, and brown for chlorine, bromine, and iodine, respectively. Alright, so there, we spent maybe 20 minutes in total there, going through them all. So, my apologies if we spent maybe a tad bit too long on that, but now you guys know it. I hope. So, you could literally get maybe 5 to 15 marks in an exam just on those questions, just on explaining stuff. Think about that. If you suck at this paper, right? Think about it this way. That is now 5 to 10 marks that you could get for just basically explaining how to test for stuff. You could probably get 20, 30 marks easily for the geography topics. You know, just for using common sense, talking about that green algae copy and paste thing. That is great. Like, you could literally get 35, 40 marks for just talking about topics, I think it's topic 7, 9, and 10. So, I guess, what do you guys want to do? Should we focus on those easy topics so that we know them off by heart? And then, you know, we'll be able to... Well, what do you guys think? Should we focus on the easy topics like chemistry of the atmosphere, using resources, so we have like a good, so that we can guarantee get all the good marks, or should we jump into some of the more complex stuff to try and, you know, get some extra stuff? What do you guys think? Because I don't mind doing either. Oh, actually, here, perfect. I've had this lying around for months, this folder full of flashcards. I guess we could do some of these. This is the one for chemical tests. If anyone wants that tomorrow, let me know. Right, I have organic chemistry, chemistry of the atmosphere, and using resources. Which one do you guys want? Which one should we go through? Using resources, chemistry of the atmosphere. I've just called this one reversible reactions, but it's actually rate of reactions, or organics. I'll give it 2 minutes so people will decide, because I'm pretty sure no one's watching now. Ashton is not online anymore. Right. I guess I'm picking. I'll roll a dice. Okay. We have 4 here. So if I get 1, 2, 3 or 4. And I got a 4, which means we're doing using resources. Okay. The only question I have here is wastewater treatment. What is it? Like, how do we do it? Now, wastewater treatment is different from making potable water, if I'm not mistaken. For wastewater, it's a bit more of, I'm pretty sure, a delicate process. So, screening occurs, which is basically where sediment is removed. And, like, the larger pieces of matter are removed. Then you have sedimentation occurs, where like it's split into layers, but I'm not sure what you call that. Then you have sludge, and then chlorination. That is my guess of what it is, because I can't remember. Let's have a look. Screening and grit removal to remove large particles. Alright, well I said screening, so we'll just add to that. We'll say large particles. Alright, there you go. That would be like 1 or 2 marks. Sedimentation, okay, yeah, there we go. Literally sedimentation. Tiny particles settle to the floor. And that provides sludge, because all the thick, goopy particles are kind of at the top, I'm pretty sure. So yeah, the tiny oh no, actually hang on, no, I'm misinformation there. The tiny particles set to the floor, and then I guess they're just scraped off and become sludge. Remember, sludge is used for like a fertilizer, I'm pretty sure, because it's just a bunch of like organic matter. Sludge is... Oh, the sludge, anaerobic digestion, I know what that is. So that's when you get like bacteria and stuff in anaerobic, remember, like respiration, no oxygen. So the sludge is eaten away by the bacteria. But I guess it could also just be used for fertilization too. 2 possible uses. Then sterilization occurs. Now this could take place in the form of chlorination. You could use ozone, which I'm pretty sure is just very concentrated oxygen. Or you could even use UV light. Problem with, I'd say, ozone and UV is it's probably very expensive upkeep. But chlorination, just add a bit of chlorine in. Remember, you kill the bacteria, you don't remove. Because if you remove a bacteria, that would be bloody magical. No, remember, all water has billions, trillions of dead bacteria and viruses and stuff in. which is kind of mad, but that's the way the news goes. Right, let me check Discord. No one said anything. So I'm assuming that we're ready to just keep going on. So yeah, that's all I got. Wastewater treatment. Although I know that making potable water is its own thing. How about we go back onto that in a little. Let's do chemistry of the atmosphere in the meantime. How about that? While we're waiting, because it's a generic topic. I'm sure most of you guys know how it goes by now. Right, early atmosphere versus our current atmosphere. So the early atmosphere consisted of three main gases. You had ammonia. That is the one that everybody forgets. If you forgot that, you're not the only one. You had obviously carbon dioxide and methane. We love our methane. And then in today's atmosphere, you have a bit more of a diverse crowd. You have argon, just, I guess, a little bit. You have nitrogen. You have oxygen. You have trace pollutants, such as CO2. You can't just say trace pollutants, you have to say trace pollutants such as CO2. And other things too, other group A gases. So that's the difference, alright? So how the hell did we go from literally being Venus, a knockoff of Venus, to over, billions of years, suddenly having all of those funky gases? Well, you could talk about a lot of stuff here. What happened to the early atmosphere? You could talk about algae. Green algae. You have to specify that it's green. Now, according to Miss Ford, you have to also say, how the green algae came to be. I think that's a lot of bullshit. Mr. McAdam didn't teach us that, so I couldn't care less about it. So green algae photosynthesize. You need to explain what that actually does. So, algae are obviously underwater. Alright, check this out. Drawing. So algae are underwater, and during rain, little trace amounts of CO2 are being absorbed into the ocean. Then, because photosynthesis, that CO2 is converted into oxygen, which slowly pollutes, you have to say pollutes, the early atmosphere with oxygen. So that's carbon dioxide. What about the others? What about ammonia? Denitrifying bacteria. That is an actual thing. Denitrifying bacteria basically just eat the ammonia, eat the nitrogen of the ammonia, and since ammonia is made out of nitrogen and hydrogen, it gives you excess hydrogen, or I guess water vapor. Then finally methane, which I guess you could just group in with CO2. The carbon is absorbed into the water and sedimentary rock. It becomes sedimentary rock. Now Mr. McCullen went into extra detail with this. You could talk about plankton and how they used the carbon as shells. When they died, the shells went to the bottom of the ocean, whereupon eventually it formed sedimentary rock and locked the carbon. That's just your extra detail, but that's it. That's really it. So now we've covered every single one. Ammonia is great. Okay, big up ammonia, because a lot of people forget about it, but it's a lot of nice marks. So, let's talk about the formation of acid rain. This is quite nice. CO2 is created from coal, oil, gas, but coal and oil also contains sulfur. Sulfur dioxide. Now, sulfur dioxide goes into the atmosphere and reacts with oxygen to form sulfur trioxide. Sulfur trioxide combines with it reacts with the water vapor to form H2SO4. That is acid rain. Acid rain corrodes away primarily metal, But also things like coastal erosion can occur because of acid rain, I'm pretty sure. Ashton will have to tell me if I'm right on that one. We also got the effects of carbon dioxide itself, which would be destruction of habitats due to flooding, because the ice caps melt, because of an increase in global temperature. Link each thing to another and you'll go high with this one. Also talk about destruction of habitats for acid rain too. Because that happens. But animals aren't used to the high pH level. Low pH technically. So they're going to die. Greenhouse. This one I need to quickly recap on. I don't even know it myself. So infrared rays of short wavelength go kaboom kaboom. The sun emits these short wavelengths and the earth absorbs them. Then the earth emits its own infrared waves, but they are of long wavelength. The atmosphere absorbs most of these waves to keep the earth warm. There are a couple that obviously escape into space, but the majority are absorbed. And by having, I guess, a thicker layer upon which these long wavelengths can, try and get through, it means that it's harder for the gases to escape, keeping the earth warmer, which is very evident right now. I'm sweating. Please help me. Right, so there you go. Chemical tests done. Chemistry of the atmosphere done. Using resources kind of done. Now let's just go through reversible reactions. This one's okay. We'll leave the evil organic chemistry topic for last. So, reversible reactions. I've got a lot of flashcards here. Right, let's get it. Conditions for the Haber process. We know this. 450 degrees Celsius, 200 atmospheres, and an iron catalyst. I'm not even going to write this next bit because you know what it is. A catalyst either provides an alternative pathway for the reaction to occur, or it reduces the activation energy required for the reaction to occur. Okay, now we need to know something called the Haber compromise. Now what that is because this reaction, I'm pretty sure, is, I wouldn't say endothermic? Basically, 450 degrees is quite a low temperature, because if it was any higher, the reaction would give you a bigger yield, but it will be slower. Because the higher, then the reaction is pushed left. It is favoured backwards instead. So this is a compromise. It's not the best solution, but it's the optimal one. 200 atmospheres, that's the max we can get, because otherwise we're going to get, the rate of reaction and a decent yield. But that's kind of it. But anything higher than this would be very expensive and it would be very dangerous. Now, for an iron catalyst, I've just said that. Okay, collision theory, the basics in this. If we increase the temperature, it means the particles are going to move around more, meaning a higher rate of collisions, which means a higher chance for a reaction to occur. If we increase the pressure, aka like a smaller little area for the particles, they're going to have less room to move around because there's more of them, increasing the rate upon which the particles collide. If we give each particle a smaller surface area, a smaller volume, it means they actually have a larger surface area, meaning more collisions. So yeah, higher frequency of collisions means higher frequency of reactions. What effect does change have on the equilibrium? We know this. If you add a reactant, it's consumed, so it goes forward, I'm pretty sure. Yep. If you add a product, it goes backwards. If you increase the pressure decreases, so there's less molecules in the system. If you decrease the pressure increases, so there's more molecules. Increase the temperature, the heat is consumed for an endothermic reaction. Decrease the temperature, the heat decreases because of an exothermic reaction. So if pressure decreases, there'll be no change if both sides have the same molecules. Finally, well, not finally, there's one. Oh yeah, Haber compromise. We've already talked through this. Reversible reactions. It's easy to know. Two simultaneous reactions occurring forwards and backwards. Alright, we are almost done, guys. In literally an hour, we have rushed through the topic, and I can't promise you that I've covered everything. You guys are going to have to do your own revision, or alternatively, watch some of the previous streams. Maybe I've covered something there. Actually, that's a terrible idea. Revision document. It'll save you plenty of time. I've added a couple things on there from a couple of weeks ago that you should check out. Bro, I've turned red. Look at this, bro. I'm not used to this heat. In fact, can I go steal my parents' fan quickly? I'll be right back. I'm going to go. I stole my mum's fan. I'm sure she won't mind. This thing's dusty as hell. This hasn't been used in months. There we go. Adding a bit of pressure. Remember, by the way, reversible reactions have to happen within a closed system. Okay. Finally, let's get on to organic chemistry, my absolute favourite. So. Oh. There's not many flashcards that I've done here. So, let me try and also improv. So. We obviously know the functional groups for alkanes, alkenes, alcohols, and carboxylic acid. Acids. So for alkanes, there is no functional group, technically. So, actually, it's better if I just draw it. CC. So remember, carbon has 4 spare electrons, like, in a sense. Its outer shell, if we draw it, there is 1, 2, 3, 4, because it's in group 4. It has 4 slots, I guess you could call them, that it can react with. And look at that, 1, 2, 3, 4, 1, 2, 3, 4. Alkenes, there is a double bond, and it's its functional group. Which means there is 1 less bond on that side. Alcohols have no double bond, but they also have OH instead. The way to go from an alkene to an alcohol is you use steam, basically hot water, and you use, I think it's a phosphoric acid, I'm pretty sure, as the catalyst. Carboxylic acid, it's COOH, so you use an oxidizing agent, because if you'll notice, you have an extra oxygen. To test for an alkene, to differentiate between these two, you use bromine, dilute bromine, because in an alkene, it will break the double bond and change its colour, but only temporarily. It will go clear eventually. This one will not go clear because it can't react. Now, those are the functional groups. Now, you do need to know maybe one or two things about flipping, what do you call it, polymerization. But I'll be honest, I'm too tired. I can't really remember anything from that. So if it comes up, it's game over. All I know is how to do, like, these. It's where you kind of cut off the arms at an N here, and then whatever else here. Now, what else do we need to know? I guess where nitrogen comes from and methane. So sorry, nitrogen comes from the air. You would fractionally distill it. Methane comes from hydrogen. Hydrogen comes from methane. Alright. So, what is crude oil? Crude oil are the remains of marine plants and animals. They sunk to the bottom of the ocean, being buried, which prevents rotting. This is a biology thing. The layers of rock slowly build up, which means there is more pressure. So these remains break down into molecules that form crude oil. Crude oil is a mixture, substances that are not chemically bonded. That's how you get things like kerosene and petroleum and all that good stuff. Now, this is fractional distillation. Remember, it's a hot bottom, a cold top, which means the different boiling points will kind of separate outward. So, hot bottom, cold top. So the ones with a high melting and boiling point will, of course, condense here. The ones with a low melting and boiling point will condense here, I'm pretty sure. So yeah, the vapors condense when they reach parts of a column that is greater than their boiling point. Liquid flows out of a column. So yeah. Then finally, cracking. Cracking is basically turning a long chain hydrocarbon into a small chain. You would use a porcelain catalyst. You would use high atmospheric temperatures. I think 700 degrees, I'm pretty sure. Let me just go Google that quickly there. So yeah, a larger saturated hydrocarbon is broken down into a smaller, more useful one. Thermal, steam, and hydro cracking, those are the differences. So yeah, the way it works is this is an awful diagram, but let's look at it anyways. So the way it works is you would heat up your oil. Okay, let me just Google conditions. So high temperatures, so yeah, 700 degrees Celsius. High pressures up to 70 atmospheres. You would also use a porcelain catalyst. There you go. That is it. I am done. I have just spent an hour almost. In fact, less than an hour. Great. We've speeded through this topic, which is great because that means now you guys have more time to revise or do what I'm gonna do, sit down and draw stuff for like an hour because I don't want to revise anymore. Look, I always go by the premise that if I understand something, I understand it. If I don't understand it, I can't teach myself it in a day. And now I literally have less than a day. In fact, I have like probably 12-ish hours. So, by that logic, good luck everyone tomorrow. Be sure to continue to stay happy, healthy, and safe. And next stream will probably be... I don't think I'm going to do a math one. I think I'll rather just revise on my own. I'm going to do an after school and stuff. Then, for physics... I couldn't care less about that, so no revision there. In terms of history, I'm probably not going to do one of them. I'll just revise on my own. So this might be the last ever revision stream. Unless I do one on Sunday for stats. No, I won't, because we'll be doing stuff in class anyways. Oh my god. This is the last ever revision stream for GCSEs, everybody. Thank you for watching. This has been great, right? I have literally been on this journey with you guys, you know what I mean, obviously. But more than that, I have literally been able to teach myself so many things that I didn't know before. Going from biology, I barely knew structure of a plant, barely knew food tests, digestion, the heart. We were able to go through all of that on stream and teach it, and now I know it off by heart, literally. Same with a lot of paper 1 chemistry stuff, and hopefully a lot of paper 2 stuff. So this has been great. I hope these streams have been helpful to you guys, because they've been really helpful for me. I find that by being able to explain something, I can teach it to myself better, because if I'm able to explain stuff right, you know, it makes things easier. Okay, hang on a minute. I think something must have blocked the chat there, because I have not been seeing any of these things for ages. Bro, can you explain in one word about empirical formula? I'll be honest, I'm just headed off. And I'll be totally honest, I'm so tired, I don't know what those... Do you mean, flipping... What do you call it? Like, molecular mass and stuff? I'm pretty sure it's like a thing on... You could probably, like, go on BBC Bite Size and stuff and find them. Because, yeah, I'm heading off. I was just doing a little outro and stuff. I think all of your things have been getting blocked, because I literally haven't seen anything. I have not been seeing any of these messages for ages. Huh. But anyways, yeah, thank you guys, because this has been great. I don't know what I'll do with all of these remaining streams. I'll probably private them all. And again, in terms of the main channel, now that we're closer than ever to July, GMC Arts will be back. I'll be back to doing weekly videos, Subscriber War Season 3, all of that good stuff. So make sure to stay tuned for that. Thank you for watching all of these revision streams, and I will be